So students, be welcome to our class 3 of the fundamentals and applications of process simulators in chemical process, okay? And in this class, in class 3, we are going to talk about chemical reactors, okay? And how to simulate most of their models in Aspen Plus, right? And then we are continuing the content of this course, okay? And in previous class, let's remember that we learned how to configure some models for fluid transport and heat transfer. Okay, and for fluid transport, we checked some configurations for simulating pumps, valves, compressors, pipes. Okay, and we solved a large example combining many of these equipment, and also we tried the most common equipment for heat transfer available in Aspen Plus, for example, for using some of them as heaters, coolers, or also a heat exchanger, as we simulate a heat exchanger with a robust method, considering a shell and tub heat exchanger, and we simulated it considering the entire geometry of the heat exchanger, considering number of tubs, the diameter of the shell of the tubs, and we configuring the heat exchanger between naphtha and kerosene in our example in our last class. Okay, so we tried two large examples, okay, in the last class. And in this class, we are going to work with more examples, but they are shorter than the examples that we solved in our last class, right? So in this class, we are going to understand the classes of reactors that we can try to simulate using software for process simulation, okay? We are going to understand how work some of the chemical reactor models available in Aspen Plus. And also we are going to understand in the first part of our class the most important equations present in these models and all the information that's required for simulation most of them. Okay, and we are going to solve some examples in the second part, in the hands-on part, as we have done in the previous classes. So first of all, let's learn here that considering Aspen Plus as our process simulator, we have here many models for simulating chemical reactors. Okay, here we have the most common reactor models present in the last version of Aspen Plus. So we have here the conversion reactor, which is also known as the R-stoic model. We also have the R-yield model, considering the yield reactor. After we have here some thermodynamic models, the equilibrium reactor and the Gibbs energy reactor. And also we have some kinetic reactors for simulating, for example, a CSTR, okay, the continuous storage tank reactor, and the PFR as the plug flow reactor, considering here this model R-plug, okay. Also have a model for batch process, for considering batch reactors, okay, it's the R-batch. And also in the most recent version of Aspen Plus, we have the model named electrolyzer, okay, for simulating the reaction of electrolysis for water electrolysis, aiming to produce hydrogen and oxygen, okay. So basically most of these reactors we have involved the molar balance and the energy balance, okay, and we are going to solve all the equations considering mass, the total mass balance, the molar balance for each compound, and the energy balance for the system, okay, will be solved once that we configure the information required for this model. Okay, so when we aim to simulate a reactor, we are trying to solve the molar and the energy balances for giving information about the composition of the products after the reactor, and also the energy required to keep constant the temperature if the reactor is isothermic, or also the amount of energy for keeping some value of temperature, or the heat of the reaction that was removed or was provided to the reactor for promoting that reaction. Okay, so we can solve these models for achieving all these results. Then let's go next. So first, let's talk about the most simple models, okay, that we have in Aspen Plus, that they are also known as stoichiometric reactors, okay. And here we have two possibilities for solving more simple balances for mass and energy balances, okay? And you can use the R-stoic model or the R-yield model, okay? So let's understand the goal of using these models first, and we are going to check each one of your reactors for practicing examples in the second part, okay? So the goal of using an R-stoic model in Aspen Plus is when we are trying to simulate uh, a process when the reaction kinetics are unknown. Okay, so we are not considering the kinetics here. And in this case, the volume is not a variable that we can try to get as a response. Okay, we need to inform this value here, and so we can use this model for projecting, for designing reactors. And also, we just need to know the stoichiometry or the fractional conversion or state of reaction for our system. Okay, if you know the stoichiometry and also we know the conversion or the state of reaction, we can specify it for calculating the amount of product that was produced and the remaining reactants that didn't react in that system. Okay, so normally it's valid when the process is controlled by fixed plant specifications for solving molar balance. Okay, when we just want to solve molar balances, so we can use our stoic model, and it's a good model for predicting, because if you do that for systems with many reactions, with many compounds, maybe using other strategies can take more time. So it's a good possibility using an R stoic model for solving systems with multiple reactions and multiple components present in that system. Okay, so here we have the molar balance for the system, considering the extension of the reaction, which has a direct relation to the conversion. And also here we are considering steady state. Okay, so what's leaving the reactor is equals what's entering into the reactor plus or less what is reacting. Okay, less if it's a reactant, and we are summing if it's a product. And here we have the energy balance, considering also steady state based on the enthalpy of the components and also calculating the energy for keeping the temperature constant or for predicting the enthalpy of our system. And here, in case of the R yield, we are using this reactor for predicting the amount of product obtained. Okay, and the difference here is that we don't need to know the stoichiometry. Okay, in this case, we also don't know the kinetics. Okay, the kinetics are unknown, but we also don't know the stoichiometry. But we know the yield of our products, or the distribution of fractions for our products, and that we have this information through empirical or experimental data. Okay, so in this case, we can just specify how much product we are obtaining for our reaction, and this reactor will try to distribute these fractions for according to the balances for the components in terms of carbons, hydrogen, oxygen that our reactants they have. Okay, so we need to know the composition of our reactants, and based on a balance of atoms, it can predict the amount of products obtained. Okay, and in this case, it's the standard model used to simulate reactors with non-conventional strings, and we are going to talk about non-conventional strings in your next classes, maybe in class 4 or class 3, and specify solids in that string or pseudo components. Also, we are have this case we have non-conventional strings, like a process for pyrolysis or gasifications of biomass or coal, for example. So we know the composition of our biomass of our coal. We want to predict the amount of products obtained, considering the yield that's possible to obtain according to experimental data or the classification and the quantification of the components in your system. Okay, when you have the characterization of our products, we can use this model. Okay, so it's based in the amount of in the yield for each component. Okay, and the yield is calculated based on the ratio between the product obtained and the reactant that was consumed for obtaining that product. So based in this relation, we can try to obtain how much we have in the output stream and based on what was fed into the input stream. So they are simple models just for predicting and solving mass balances, or maybe estimating the energy according to the enthalpy of these reactors. So these are not models that are used for designing reactors or for getting more specified information about our reactors. So these are the main equations present in this kind of reactors. Next, let's talk about the models that are known as thermodynamic reactors. And in this case, we have two models present in Aspen Plus, the RAQ and the R-Gibbs models. Okay, so basically we use this kind of reactor when we have a system where the thermodynamics are limiting the conversion of our system, and maybe is used for fast reactions that we don't need to take into account the time or the kinetics for achieving the equilibrium conversion. Okay, so we have here just a little bit of some difference between on the model the mode of calculating the equilibrium for both models, and also in one of them we need to specify the reactions, and in the other model it can try to understand and to access the possibilities of the reactions without specifying the reactions. Okay, so first for the RAQ model, it models reactions that reach chemical and phase equilibrium. Okay, so we also can use it for systems with two or more phases. Okay, and it's ideal for fast reactions at high temperatures where kinetics is not the limiting factor. Okay, for combustion systems, for example, and also other systems that their reaction is pretty fast. Okay, the main equations that we use here is the first equation here for calculating the equilibrium constant. Okay, based on the coefficients and the activities of the compounds present in our system, and also for calculating the constant of equilibrium, it's also calculated the variation of Gibbs energy. Okay, based on this equilibrium constant. And with this minimum of energy, we can try to understand the state of our system and what's the composition that we have in that state. Okay, because once defined its temperature and pressure, there is only one possibility for composition for solving the thermodynamic equations for that system, right? And the R-Gibbs model, in this model, we don't need to specify the reactions in stoichiometry. Okay, in the first one we need to specify, and you need to work only with the reactions that we specified, calculating the constant of equilibrium for each one of them. And in this other model here, we can specify just the compounds that are present in our system, and based in the compounds and the possibilities of compositions for that compounds in that state of temperature and pressure, for example, the software predicts the outlet composition by minimizing the total Gibbs free energy of the system. So it works solving an optimization problem, in which the optimization problem is to minimize the energy Gibbs, the Gibbs free energy of our system. Okay, and also it's objected to having the constraints here for considering closing the mass balances, the energy balances. So here is also need to get the balance for atoms of or the compounds present in our system. And it's widely used in reforming and gasification reactions where dozens of simultaneous reactions occur. Okay, so when you have many reactions or possibilities in our system, it's a good model for applying and predicting the products in this kind of situation. So next, the other possibilities that we have for simulating some reactors here, okay? They are the kinetic reactors, okay? And in this case, you have two main kinds of reactors, as students of chemical engineering or chemical engineers, you know, that we can try to use a model considering, in this case, concentrated parameters, okay? And lumped parameters, we can try using a CSTR. Okay, it's a storage tank, continuous storage tank reactor, and it simulates continuous process where the reaction kinetics are perfectly known, assuming that the reactor's constants are perfectly mixed. That means we have a uniform temperature and concentrations through the volume. Okay, So this is the main equation obtained from the molar balance in this reactor, okay? And you can see here that we need to know the kinetic rate for our reactions to calculate the volume of the reactor, and it can be used for designing reactors, okay? And this expression, this rate expression for the kinetics, it has, we can use for it many possibilities, okay? We can use the power law model, we can use the Langmuir-Hishing-Wood-Hugen-Watson model, or we can use different models for predicting this rate of the kinetics. Or we can use the air-plug model, okay, which is a reactor in which you have distributed parameters, okay, and it simulates continuous flows in pipes where kinetics are known, assuming no axial mixing in this case, okay, so we have a plug flow state and perfect radial mixing. Okay, in the model present in Aspen, we are considering only the profile in the axial direction. Okay, so we don't have some profiles in the radial direction. And it's the standard model for gas phase tubular reactors, fixed bed catalytic reactions, etc. Okay, so we have here some possibilities of simulating reactors that we must know the kinetics, okay, the kinetics expression for compounds, and here it's a differential balance, okay, and we are calculating the composition, the temperature, or the pressure in each point of our reactor along the size, along the length of this reactor. Okay, so in this case, for simulating these reactors, that maybe is the most common or most used models, in this case, we must know the kinetic of our system, right? So we also can use the other two models that I have commented in the beginning of our presentation, okay? We can use the R-batch model for simulating batch system or semi-batch systems, okay? When we have the variation with time of the components inside our reactor. So we have here the mass balance with all terms, okay? We have here the accumulation term, the reaction term, and the inlet term and the output term, okay? So we can try to calculate these variations with time inside the reactor, okay? And it requires knowledge of the reaction kinetics and models how composition and temperature vary as a function of time, okay, rather than special time, okay? As we just have just saw in the air-plug model, okay, that we have the spatial variation. In this case, we have the time variation, okay? And we are trying to understand how much time I need to operate that reactor for achieving some conversion, or if I have some time of operation, what will be the conversion after that time? So I can answer questions about that, considering a system that's simulated as a batch or a semi-batch reactor. And finally, we have here the electrolyzer. As I said, that's the model used for production of hydrogen mainly, in which it's occurring the electrolysis of water. Okay, it's a reaction that can, it's very studied in many parts of process modeling and simulation course. Okay, because today's producing hydrogen is very important for many scenarios. Okay, and we have different kinds of electrolyzers, and for each one of them, maybe you have different equations, or we have different efficiencies and parameters for predicting the amount of hydrogen produced. Okay, so this model of a reactor in Aspen Plus, it simulates electrochemical behavior, calculating electrical power consumption, cell efficiency, and gas production based on polarization curves and Faraday's laws. Okay, so in some cases, we can also specify some experimental data for predicting the efficiency or the energy power consumption for electrolyzing and producing gases as hydrogen and oxygen. And normally it's used for modeling water electrolysis, as I said, and here we have the main kinds of electrolyzers, okay? The PEN, okay, using membranes, in this case, the alkaline electrolyzer, and also the SOIC electrolyzer, which uses solid states models for hydrogen production, and it's focused on green hydrogen production. Okay, when you are talking about electrolysis of water, so it depends of the energy that we are providing for promoting the electrolysis in the reactor. We can classify the class of hydrogen that's being produced. So we have here a balance for amount of hydrogen produced based in the number of cells and other parameters in this reactor that we are going to check later. And here we can also see the voltage of the cell, taking into account here some efficiency that we can observe according to the characteristics of this reactor. Okay, so in here we have some all models of reactors present in Aspen Plus. Okay, so here we have the Faraday's law and the cell voltage equation, as I said, for electrolyzer for predicting the amount of energy produced. Okay, next, let's check the main parameters that we must specify for using each one of these reactors. Okay, so for the Aristotle model, the purpose of simulating case considering this model is to model reactions when the exact kinetics are unknown or unnecessary, but the reaction stoichiometry and fractional conversion or state of reaction of a reactant are known. Okay, as I explained earlier. Okay, so we are trying only solve mass balance or molar balance. So we must specify for simulating this model the inlet stream condition. Okay, always we must specify these conditions. And also operating conditions. Okay, the temperature, pressure, heat density, or vapor fraction. For establishing the thermodynamic state of the compositions or the reactor, we must specify always two of these conditions. Okay, for specifying the thermodynamic state, can specify temperature and pressure, or can specify temperature and vapor fraction, and we can calculate the other conditions because when two variables of these variables are specified, we achieve 0 degrees of freedom for solving the flash calculation for that condition. Okay, we must specify the stoichiometry of the reactions. We must specify the fractional conversion of a reactant. Okay, and also we can specify the reaction valid phases. Okay, because depending here on the temperature and pressure, now of course some components they can be in different phases, or we can specify that we are working only one phase is valid. Okay, for unconsidering other parameters in other phase. Okay, we want the balance for only one phase, and you can specify this important information in this model. So for the R-use model, okay, so the purpose, let's remember, is to model a reactor when we don't know the kinetics and we don't know the stoichiometry, but we have experimental data or data from literature that we can use for predicting the amount of products produced, and it's the go-to model for simulating the breakdown of biomasses, coal, or solid waste. So normally when you have some compounds with composition that's hard to estimate, or we know only the amount of atoms of each element in that composition, we can use it trying to predict the products based on experimental data. So we need to specify the inlet stream condition, the operating conditions also, as we just saw for the stoichiometry model, okay? And we must specify the yield distribution for all expected products. Okay, for example, for producing biogas, I can specify the composition of my biomass in terms of approximate analysis and other final analysis. And we can, based on the characterization, we can try to specify how much methane is produced, or how much carbon dioxide, methane, and other compounds I have in the biogas. And it will try to estimate how much of the mass fed into the reactor is converted in biogas and how much is converted in the digestate or the other co-products from that system. Okay? And we also must specify reaction valid phases for simulating this kind of reactor. Okay? So these two are the conversion models for reactors as we discussed. Next, let's see the information required for the thermodynamic models. Okay, the first one, the RAQ. Okay, that is, it calculates the constant of equilibrium for each one of the reactions, and after it can estimate the variation of Gibbs energy. Okay, and this model, it model reactions that are fast enough to reach chemical and phase equilibrium under the reactor conditions. So the kinetics is not important because the reaction is pretty fast. And it calculates the equilibrium composition based on the specific reactions. So we specify the reactions that we are considering, that are taken into account, and we specify the inlet stream condition, operating conditions, the temperature, pressure, heat density, vapor fraction, and we can specify here the stoichiometry for all possible reactions that are occurring in the system. Okay, and it will take into account that reactions, it will calculate the constant of equilibrium for each one of them, and with it, it can calculate the equilibrium state based on the zero variation of Gibbs energy, which is related to the equilibrium state for our system. Okay. Also, in some cases, we can specify the temperature near equilibrium as an initial guess that maybe can facilitate the convergence of the simulation. Okay, and we can specify also the reaction value phases. So the other thermodynamic model that we have there are Gibbs. Okay, and the difference, as we discussed it, is that in this case, we can determine the chemical and phase equilibrium without specifying the reaction stoichiometry. Okay, because it will identify all components that we have selected, and it will arrange all the possibilities of reactions that we can have, taking them as reactants and products, and based in this composition, in these components, it will calculate the equilibrium condition that's possible to achieve for that compounds, okay, in that conditions of temperature and pressure, for example. And it's ideal for highly complex reactive systems where multiple reactions occur simultaneously, okay? So we don't need to specify all reactions and which reactions are occurring in parallel or in series, so we can specify only the compounds, and it will calculate the composition in the equilibrium based in the thermodynamic state that's possible for that system, minimizing the free energy Gibbs energy. Okay, we must specify the inlet stream condition. Okay, what we are inserting into the reactor, the operating conditions, as we saw for the other models. We can select the calculation option if we are trying to solve only with phase equilibrium or only with chemical equilibrium, or both, or if you are considering phase and chemical equilibrium. Okay, we can also include the valid phases. We can include solids, okay, in this case, as possible products. And we also can specify a list of possible chemical species that could be formed through the reaction. Okay, we can specify for facilitating maybe or for restricting our simulation, but if you don't need to inform, if you don't inform, it will take into account all possibilities, right? So next, for the continuous stirred tank reactor, okay, as we discussed, it's used to simulate a continuous process where the reactions are known. So we know the rate of production or the rate of consumption, and we can specify different models for this rate. Okay, we can specify a power law, we can specify L88 and W model, we can specify different models, and we have the assumption that we have a perfect mix. Okay, so we must specify the inlet stream conditions, the operating conditions, the detailed kinetic reaction rate expressions. Okay, we must specify, for example, the parameters for the Arrhenius law, okay, as the activation energy, the per-exponential term for predicting the velocity of the reaction in that temperature, okay, the concentration dependencies, if the reactions there is only the forward reaction, or if you have the reverse reaction with effects in our system, the valid phases, and also for designing the reactor, we can specify or calculate some sizing parameters as the volume and the residence time. Okay, we can use it then in the equations for the mass balance as we have seen in the previous slides. For the our plug model, okay, it's the plug flow reactor model. We are trying to simulate the reactions through a pipe or a tub where kinetics are known. And we are assuming no axial mixing, okay, but we have here a perfect radial mixing. It's why we use it for gas phase tubular or fixed bed catalytic reactors, okay. And in this case, we are going to check how our reaction is occurring along the length of the reactor, okay. And in this case, we must specify the inlet stream condition, operating conditions, detail the kinetic rate expression, specify the geometry and sizing of the reactor, for example, the number of tubs, the length, the diameter of the tubs, the catalytic properties, for example, particle density, bed voltage, or mass of catalyst present in the reactor for a packed bed, because with this information we can calculate what's the volume that's available for the reaction, okay, because if you have something inside the reactor, it's not all the volume that will be available for the reaction. And we can select some calculation options considering, for example, if the reactor is adiabatic or if it's an isothermal system, or if you have some external fluid for heat transfer, removing or adding energy to our system. Okay, so this is other possibility that we can try to simulate with this model in Aspen Plus. So the next model, the R batch model, okay, we are trying to simulate a batch or a semi-batch process. Okay, it's a batch process is the process that we keep all reactants in the reactor and we wait until the reaction ends to keep the products from the reactor. Okay, but the semi-batch process is that process that you can insert some products in the reactor in the beginning, and we can only insert other reactors or remove some products from the reactor along the time, considering that you are not feeding and removing at the same time. Okay, we are only feeding the reactor or we are only removing, we have a same batch condition. Okay, and we must specify the reaction kinetics, and it's used to study how concentration and temperature profiles evolve over time. Okay, so we can predict the timing for achieving the equilibrium conversion, or we can try to understand how the concentration is ranging along the time, how the temperature is ranging along the time, the reactor, or if you are planning many batches, we can specify how many time I'm going to consider for each one of the batches, and we can answer questions that with the other models we can't answer. Okay. In this case, we must specify the inlet stream conditions, the flows of the reactants, the composition, the temperature, pressure, the operating conditions, the tailored kinetic rate expressions. Okay, in this case, kinetic rate expressions considering the variation of time, initial charge conditions. Okay, because in this case, as we are going to solve ordinary differential equation, we must specify the initial conditions for solving this problem. The stop criteria, if it's the batch time or is a target conversion rate. And for a semi-batch, we must specify the feed stream conditions and flow rates over time that are being fed into the reactor along the batch. Okay, so it's a model for simulating batch process. And finally here, we are going to understand the purpose of using the electrolyzer with an specified model, as we have discussed. It's used only for producing hydrogen normally. Okay, it was added to Aspen Plus only in the most recent versions. Okay, and it's used to rigorously simulate electrochemical cells for hydrogen generation, considering different technologies of electrolyzers. We have the PEN technology, considering here an electrolyzer with membranes, the alkaline electrolyzer with some alkaline fluids that are used for promoting the reaction of electrolysis, and the solid state electrolyzer that's known as SOIC. Okay? And it calculates the required electrical power, the thermal energy balance, and the gas production rates based on electrochemical principles. Okay, so we consider more detailed models, more detailed variables involved in the electrochemical reactions here for producing hydrogen. Okay, in this case, we consider that there is an anode, a cathode, and we have different reactions occurring in each one of these parts of the electrolyzer. Okay, and we must specify here the inlet stream conditions, the operating conditions, the cell technology type, because depending on it, it has maybe some particular parameters, the system design parameters, the number of cells present in the electrolyzer, the active cell area, the area available for producing the gases, some electrical input for considering the efficiency of producing the gases, as the current density or total power, and some electrochemical parameters, as for example, polarization curve coefficients for the system, or empirical data. And with this empirical data, we can calculate the coefficients for the polarization curve. Okay, so this is a model that specifies for producing hydrogen, and some students, mainly because of the energy transition, are considering simulating scenarios where this model is present in nowadays. Okay, so also in this class, okay, we are going to simulate 6 models. Okay, we are going to simulate the first 6 models that I have presented to you in this class with some examples. Okay, so we have 6 examples in this class, and we also are going to understand how to use a tool that's a very powerful tool present in Aspen Plus. Okay, and we are going to understand how to promote a sensitivity analysis in the software. Okay, so let's understand what is the sensitivity analysis, because in some examples we'll be applying this tool, this technique, for predicting different cases or for simulating different conditions based on the case study. Okay, so the sensitivity analysis is an evaluation technique that seeks to estimate a model's output parameters based on fluctuations in determining variables, input parameters. In other words, sensitivity analysis involves running multiple simulations using various values for the different input variables to understand the effect each one has on the process model by analyzing the resulting response. Okay, so here we have an image, okay, and it's present that here we have many input variables, okay, and that will be based on that input variables, the simulation will calculate the output variables. And here we have many output variables being calculated by the simulation, okay, based on our model and the parameters that were specified. So the sensitivity analysis try to vary some variable here, trying to understand the effect of this variable in other output variables in the exit or in the response of our model. Okay, so for example, instead of carrying many simulations, we can just specify the variation for the input variable, and it automatically will calculate all cases for the variations of our input variable. Okay, for example, we are going to test different reactors with different volumes. I have the standard volume of 3 cubic meters, for example, and I want to access the conversion of the reactor considering cases when it has 1 cubic meters, 2, 3, 4, 5. I don't need to perform many simulations. I can specify the interval that I want to access my input variable, the range that or the step that I'm using between each case, and I'm going to access my conversion, for example, for each one of that cases. Okay, so this is a sensitivity analysis. A sensitivity analysis, we are going to solve multiple scenarios using this tool without it to running one by one, and you can plot these results in the file. Okay, so it's a very nice tool that we are going to learn how to use it in some examples today, right? So next we are going to our hands-on part of the course. Okay, so we have now all the examples, 6 examples that are available for you in our Google Classroom. So you can open Aspen Plus. Okay, let's solve all examples. Okay, watching the video and performing all the procedures step by step, one by one at your own time, for solving the case studies that I prepared for you today. Okay, and here we have the description of the examples next, but I will be always reading them with you in the videos. Okay, so we have now 2 hours for solving the examples of reactors, and when you finish, okay, you have here a close of our class. Okay, just comment some some possibilities and some questions, and we can finish it after finishing this time. Okay, and also I will be making available the quiz 3 for you in the classroom. I think it was not available yet, but I will be giving his for you now in your classroom. Okay, and you can answer after the examples. Okay. So, do you have some questions? Do you have some doubts about the content? Can you share a question if you have some question? No? If you have questions, you can send in your Google Meet chat, okay? And I will be checking along our class. Let's solve examples 1, 2, 3, 4, 5, and 6 next, okay? And you can now start solving the examples. And if you have questions, just ask me here in person. Students can call me, or here you can send questions in the chat, okay? So let's go to our examples. And if you have questions, please send them here in our chat. Okay, so let's go now to our Google Meet and let's solve our examples considering different reactor models in Aspen Plus. Okay, so see you soon. You can start example 1. In example 1, we are going to execute the simulation of the stoic model, okay, for a conversion reactor. In this example, let's first to understand what we are going to simulate, and next we go to Aspen to prepare the simulation, okay? So ethylene glycol is produced by the direct hydration of ethylene oxide, okay, which is this first reaction here, and the reaction proceeds in the liquid phase without a catalyst at 200 Celsius degree. In addition to the hydration of ethylene oxide to ethylene glycol, subsequent hydroxyalkylation can also occur, leading to the formation of diethylene glycol or higher glycols. Okay, and this is the second reaction representing this another possibility. To prevent these subsequent reactions, the process is carried out with a significant excess of water. In this example, we consider the following reaction and side reaction with the given conversions. So, 95% of the ethylene glycol of our ethylene oxide will be being processed in reaction 1, and 5% is going to be processed being converted in reaction 2. Okay? So, the molar ratio of ethylene oxide to water is 1 to 12. Okay, so this is going to be the ratio for the feed streams that we are going to feed into the reactor. And the ethylene oxide and water enter the reactor at 25 Celsius degree and 3 megapascal. The reactor temperature is 200 Celsius degree and the pressure is 3 megapascal. Okay, use the non-random to liquid Redlich-Kwong thermodynamic model. That means non-random to liquid for coefficient of activity and Redlich-Kwong for fugacity and coefficient of fugacity. Okay, for the system, and we will be using Aspen Plus to calculate the composition of the reaction products. The reactor heat dot if 100 kmol per hour of ethylene oxide is processed. Okay, that means if this is the amount for ethylene oxide, 12 times this is the amount for water, right? And the heat of reaction for both reactions if the reference temperature is 25 Celsius degree and the reference pressure is 101.325 kilopascals. Okay, and the reference phase is liquid phase to promote this reaction. So next, let's go to Aspen Plus for simulating this case study. Let's go to our simulation. So here, let's create a new simulation, right? And first of all, let's select our compounds, ethylene oxide, our main reactant. Let's find here as equals, okay, to not find the other possibilities similar to this compound. Water, remember clicking add instead of replace, okay. Ethylene glycol as our main product. I think we don't find it here. Let's check using contains. Ethylene glycol here. And the diethylene glycol for the second reaction. Be careful here selecting the appropriate component, because you have other variations of diethylene glycol. Okay, we can try by the molecular formula, okay, which is here, I think, C2. Let me try in a different way. Here, diethylene glycol, okay. So we have selected all components. Next, as our methods, let's filter using null here, and let's find the possibility of non-random to liquid Illich-Pong. Let's click next for estimating all properties and binary coefficients for iterations between each compound for this model. Okay, we need to be predicted here, so all properties could be calculated. Okay, but if something is missing, let's select for estimating the missing parameters. Okay, so let's go next and create our flow sheet, selecting our reactor as, no, it's not this model. We are going to start using a stoic model. Let's create a feed stream, a product stream. Okay, I will change the name here for defining this model. We have here the input stream and the output stream. Let's define our variables. In our input stream, let's put our conditions that we must check here. The conditions for the input stream entering the reactor is 25 Celsius degree in 3 megapascal. 25 Celsius degree in 3 megapascal. Let's change here for megapascal first. The ratio between ethylene oxide and water is 1 to 12. So if you have 100 kilomoles per hour of ethylene oxide, you have 1,200 kilomoles per hour of water. Okay, so let's select and define that based in the molar flow. So for the ethylene oxide 100, and for water 1,200. Okay, so we define in here the conditions for the feed stream. Now for the reactor, we're going to define the temperature to 200 Celsius degree in 3 megapascal for pressure. Okay, so this is the temperature and this is the pressure, right? And let's define here our reactions. Okay, we are going to select here our compound that are reacting, oxide, ethylene, and water. I think the reactions is 1 to 1, and pay attention of selecting negative values for the coefficients of the reactants. Okay, yes, it's all 1 to 1. And here we have the production of our ethylene glycol. So the conversion for the first reaction is 0.95% for the ethylene oxide, okay, which is our reference compound. So let's go next and define a second reaction in which the ethylene glycol can also react with the oxide ethylene, producing the ethylene glycol. Okay, so this our product will be reacting with our other reactant here, producing the ethylene glycol. Okay, and the conversion is 5% for the same base component with the ethylene oxide. Okay, so here we have defined both reactions. Okay, so I think all of our variables are defined. Let's click run here for looking for our result. Results available. Let's check our results. So first, the first result is the composition of the reaction products. So we can check here, clicking in the products string and checking here the composition in mole fraction or mass fractions, and we can check that all ethylene oxide was consumed as was expected, because summing the conversion fraction for both reactions we have 100% of conversion, and we produced here our products, the ethylene glycol and the ethylene glycol. Okay, so this is the composition here in molar basis and here in mass basis. Okay, we can check here in units of flows, kilograms per hour or kilomoles per hour. Okay, so this is the results for the compositions in the output stream. The reactor heat dot. Okay, the reactor heat dot. This information we can find in the block of the reactor. The results here have the heat dot. You can change here for checking a different unit if you want. But this is the heat dot amount for processing the reactor in an isothermic condition, okay, because we define in 200 Celsius degree as the temperature of our reactor, so this heat that must be provided for this reaction, okay, for keeping the temperature constant in the reactor. And also the heat of reaction for both reactions if the reference temperature are the standard conditions, okay, and the liquid phases they are reference. Okay, we didn't define the liquid phase as the main condition, but we can define it here if you want. But as no vapor phase was present here, so I believe the reactor considered only liquid phase, okay, for the reaction. And here we have the option heat of reaction. Okay, we can check here for calculate, report the calculate heat of reaction. Okay, and we must select here a reference compound. We are going to select ethylene oxide for both reactions. Okay, so for reaction 1 and for reaction 2, and these are the standard conditions that we are going to select for predicting the heat of a reaction. Okay, in this guide we can calculate in these conditions. Okay, and if select this here, we are going to calculate the heat of a reaction. Probably in our results here for reactions we have here the calculated heat of a reaction per this amount of for these reactions, considering the reference compound per mole or per kilomole here, I think per mole of ethylene oxide that reacted in each one of the reactions. So we answered all our questions and we have these results that they are valuable results for simulating a model of the R-stoic model. Okay, remember saving your simulation, and let's go next for the next example. Okay, next, in example 2, we're going to simulate an yield model, okay, a reactor based in the yield of products obtained by the reactions, and let's understand here a case study for practicing this model in Masspen Plus. A petrochemical plant aims to upgrade a liquid stream of heavy naphtha, okay, modeled as pure and decaying, into high-value light olefins, primarily ethylene and propylene. The liquid feed at ambient conditions, that means 25 Celsius degree and 1 bar, must be first be pumped to process pressure and routed through a fire heater. It then enters a high temperature cracking furnace operating at 800 Celsius degree and 1.5 bar. Okay, this furnace is going to be our reactor. Because thermal cracking involves hundreds of complex free radical reaction pathways and intermediate species, establishing a rigorous kinetic or stoichiometric model is impractical for this scope study. However, the engineering team has highly reliable mass yield percentage derived from a laboratory pilot unit. To simulate this accurately without needing chemical reactions equations, they will use a yield reactor. This model will force the inlet mass to break down it into the exact empirical product distribution specified by the engineers. Finally, the extremely hot cracked gas mixture must be happily quenched and cooled to 30 Celsius degree. This cooling process partially condenses the heavier unreacted hydrocarbons, allowing the available light olefin gases to be separated and recovered from the top of a vapor liquid flash drum. Okay, we are not going to simulate this flash drum because it's an operation that we are going to learn in the next class. Okay, so in the next class we can simulate this flash. Okay, after this model we are going to be concentrated in the reactor here and also the pump and heater operations to remember the content of our last class. Okay, so here we have the information for simulating the process, the mass flow rates, the pump data, okay, the reactor yield data, okay, the amount of products that will be obtained and the remaining unreacted and decay. And the goal of building this Aspen Plus simulation is to evaluate the technical mass balance and energy requirements of this cracking loop. Then determine the total thermal duty, the combined heat required by the fire heater and the endothermic cracking reactor to reach and maintain at 800 Celsius degree. Okay, so here we also have the specific informations of temperatures, pressures, and also efficiencies for promoting the pumping and the heating before the reactor and the specifications for the reactor. Okay, so next we are going to simulate this case study in Aspen Plus, and let's consider the proper method Peggy-Robson, considering only gas phase, okay, as the equation states, that is the standard for hydrocarbon processing in higher conditions of temperature. Okay, so let's go to Aspen to simulate this process. So first, let's select our compounds. Okay, so here we have hydrogen as one of our products. Let's add hydrogen, let's select methane. Ethylene. Propylene. And NDK, which is our reactant, right? Let's select our proper model as Peggy-Robson. Okay, so we have here in this model, let's change our filter for all, okay, for finding only the model for Peggy-Robson. Okay, let's select estimation of missing parameters. Okay, and probably it can use Unifac or Uniquac for estimating these properties. Okay, so with all these properties, let's go to simulation, and here let's find as our model the R yield model, and let's insert our strings. Here our input string, and here our product string. Okay, let's look for our conditions, remembering that previous to reactor we have here a pumping and also a heater. Okay, I forgot to insert then here, so I'm going to insert now, and I will insert here the string in the connections. Let's select this string and change reconnect source. Okay, for reconnecting it here. Okay, so we have here the heater, and here we have the pump. Okay, let's check our conditions for configuring our simulation. So we have here the basis, in mass basis of mass flow rate equals to 5,000 kilograms per hour of NDK, and let's consider ambient conditions for this process. Okay, so let's consider 25 Celsius degree, 1 bar. Let's consider our feed string as mass basis 5,000, okay, kilograms per hour. Okay, so this is our feed conditions, our global feed conditions. For pump, let's consider a discharge of 1,5 bar. Okay, an efficiency for pumping here as an isentropic efficiency of 0.75. Okay, this is the condition also that we have specified here, and for driver efficiency 0.95, as we discussed in the previous class the meaning of these efficiencies. Okay, for the heater, let's configure the temperature as only vapor phase, considering 800 Celsius degree our final temperature. At the same pressure that leave at the pump, and vapor only in this condition. Okay. Now here are yields. Let's check and configure the conditions at the feed string. I think 800 Celsius degree and 1.5 bar, considering vapor phase, vapor only. Okay. Let's check here that we have these conditions and this yield 10, 15, 35, 20 and 20%. Okay, let's configure this yield for each one of our components. Okay, so I think 10, 15, 35, 20 and 20. Okay, let me just to confirm it here, and here we have the yields for all components. I think it was established in mass base instead of molar basis. Okay, also because our basic calculations are being the amount of mass fed into the process. So I think everything is okay. Let's try run our simulation, and let's try to check what's going to happen for our results. Okay, we have here one warning that we can check for our reactor. Okay, maybe check it, it's not possible to finish the mass balance to hydrogen and carbon, but let's check the results for checking the amounts produced. Okay, it's possible that's not going to close exactly perfectly the mass balance, but that happens because we're going to use empirical data based on the amounts defined for the products. Okay, so maybe it's not exactly this amount of remaining in the cane, could be a mix of other products with other amounts of hydrocarbons that may be close to this total amount of in the cane. But we can see here that at the exit we have the same mass that was fed into the reactor. Okay, so here we have the composition, and with this we can, based in the energy for the reactions, try to estimate and answer the question here. The combined heat required by the fired heater, and then the thermic cracking reactor to heat and maintain 800 Celsius degree. So for the heater, we can find here in the results of the heater, we have here the total heat duct, and we can try to convert to the units that we want to access. Okay, this is the amount in kilowatts or gigacalories per hour. And for the reactor, we have here for block Q results this amount of heat duct in gigacalories per hour or kilowatts. Okay, so it's not a problem here, this warning, because that's common for our huge reactors, because our huge models, because you are going to determine it based in yield. Okay, so some cases some atoms could not be balanced perfectly, but the total amount of mass is balanced. Okay, so we have here finished our simulation and check at the results. If you have the combined result, you can sum the amounts that you have just checked here. Okay, so this is it for this model. Let's go to our next case study. Next, in example 3, we are going to simulate a reactor using the REQ model, okay, the equilibrium model reactor in Aspen Plus. And let's first understand what we are going to simulate and the conditions and the reactions, and in the final we are going to apply the sensitivity analysis tool in Aspen Plus to check some variations in some parameters. Okay, so let's first understand our example. The following two reactions occur in a production of synthesis gas from natural gas. Okay, so here methane as part of natural gas is reacting here with steam to produce hydrogen and CO, and carbon monoxide. And also we have here a parallel reaction of carbon monoxide reacting with steam, producing hydrogen and carbon dioxide. Okay, the first reaction is reforming, and the second reaction is known as the water gas shifting reaction, in which more hydrogen is produced and CO is converted into CO2. Let's try to model these reactions as equilibrium reactions in Aspen Plus to calculate the equilibrium constant, and let's use the Gibbs free energy method in this model. Okay, so this is the method for calculating the amount of products for the equilibrium, but we are using here the equilibrium model. Okay, so maybe it's confusing, but do not confuse the model of solving the problem with the model of the reactor. Okay, for this calculation, consider natural gas as pure methane fed into the reactor at 400 Celsius degree and 34 bar. Its preheated steam is fed at 280 Celsius degree and 34 bar as the other reactant, and the molar flow rate of methane is 90 kmol per hour, and that of steam is 235 kmol per hour. Calculate the product composition for a reactor temperature of 900 Celsius degree and a pressure of 34 bar. The thermodynamic model used Spenge-Robinson. Okay, and let's simulate this case study. And after simulating, let's perform a sensitivity analysis to determine the composition of the products in the vapor phase, as the reactor temperature varies from 350 Celsius degree to 900 Celsius degree in 550 Celsius degree increments at a constant pressure of 34 bar. Okay, so let's first solve the model, the simulation, and after we perform the sensitivity analysis. So let's go there. So first of all, let's select our compounds. Okay, first let's search for methane here. Also water representing the steam in the methane reforming. Okay, let me find here as equals, okay, to not find similar compounds. Let's find carbon monoxide, carbon dioxide, and hydrogen. So let me check if these are our compounds here. Let's select Maggie Robinson as our method. Okay, let's change the filter for all. Let's find here Maggie Robinson model. I will ask for estimating missing parameters, and let's calculate here the parameters and the binary coefficients for iterations in calculation of properties and equilibrium. Okay, let's go to simulation. Now in simulation, let's select equilibrium reactor. Okay, I will change here the name. I will insert our input stream. Check here, pay attention that the reactor has two outputs, okay? An output for liquid products, another output for vapor products, okay? Same that we are going to have only one phase in your products, it's necessary to insert both streams, okay? And if you have two phases, automatically this reactor will separate and you identify the amount of compounds in each one of our phase, okay? But we need to insert both phases, same that we are not going to have one of the phases, okay? So in case the reaction can produce only gas, so the liquid stream will be equal to 0, okay? But it has no problem. That's how this model works. Okay, let's configure first our reactions of methane here and of water, okay, of steam. I'm going to select if, as we have different conditions, okay, for the feed stream. Here in this case, we are going to insert first a mixer, okay, for mixing steam and methane, and after the mixture of both reactants in different conditions will be fed into the reactor, okay? So that's why we're going to use a mixer here, because our operating conditions for the reactants, they are different, okay? So just check if you have here this model present here in mixer splitter. Select mixer for mixing streams previous to the fed of the reactor, okay? So for methane, I need to configure its conditions. In this stream, the methane conditions is 400 Celsius degree and 34 bar, okay? So these are the conditions, and here we have a molar flow equivalent to 90 kilomole per hour, okay? So this is the condition for feeding the methane. For steam, the condition is different. Here, temperature 208 Celsius degree and 34 bar, and 280 Celsius degree, 34 bar, and molar flow rate of 235 kilomoles per hour. So I think these are the conditions, okay? Okay, so these are the conditions. They are mixed here and they go to the reactor, and in the reactor here we have the operating conditions that must be supplied some energy for reaching this temperature of 900 Celsius degree and a pressure of 34 bar. And let's consider only, in our case, vapor fraction, okay, because it's a reaction for vapor phase. And let's insert our reactions of methane reacting here with water, producing in amounts 1131, hydrogen and carbon monoxide. Okay, I think it's it. Yes. These are our conditions here. We can search a temperature approach if you want, but it's not necessary. Okay, just an estimative for simulation for better getting a better convergence or a faster convergence. Okay, but it's not necessary. I will not insert it. Next, I will select here the carbon monoxide reacting with water, producing hydrogen and carbon dioxide. That's it. Yes, 1111. Always that the reaction is balanced. Here it gives you a blue check. Okay, so if there is no blue check, that means that your reaction is unbalanced. Okay. Well, I think all conditions were specified. Let's try click next and run our simulation, and let's check our results. It processed and results available. Okay, so let's check here in our output stream. We can check the molar fractions here for the equilibrium condition in equilibrium conversion, which makes sense for combustion reactions or reactions that happen really fast. Okay, this is the maximum possible amount of production considering molar fractions or mass fractions for these reactions here, and we specified only these two reactions possible as possible reactions in your system. Okay, so other requirement is create a sensitivity analysis. Okay, I will create here a new case, and I will, in this case, I'm going to vary our reactor temperature, I think here between 350 to 900 Celsius degree. Okay, and let's access the compositions of our products here, both these three compounds. So let's create here a new variable. I will select this variable as a block var, as is the temperature of the reactor. Our block is the reactor. Our variable in this case is the temperature. Our starting point is 250. Our last point is 900. Increments of 50 Celsius degree. Let's check here our variables in the output. I will call this one 82. I'll select as a string var because it's the molar fraction or the mass fraction of a compound in the output string. Let me just check if this knows the S2 string. Okay, so S2 string, our compound in this case is hydrogen. I will create other variable for carbon monoxide, accessing it as a molar fraction, in steam S2, considering production here of carbon monoxide, and finally another variable for accessing the fraction of CO2 in one string. The variable is the molar fraction, string S2. The mixed string is the type of our string. We are going to discuss this next in the next classes. Okay, and here our variable is the CO2. Let's fill variables for selecting our three variables, and let's run our sensitivity analysis to access our results. So results available, we can see here in a table form, and all cases were they converged in simulations. This is the temperature for each one of them, and here is the amount of hydrogen, CO2 and CO and CO2 for each one of our cases in the case study. Okay, let's plot here. I will check temperature in axis X and in axis Y, hydrogen, carbon monoxide and carbon dioxide, and let's plot this graphic to understand that here we have a maximum of CO2 production in this condition. The hydrogen is increasing with the temperature in the reactor if I change and I select different temperatures for this reactor, and also the CO2 is increasing in this interval. Okay, so I hope you enjoyed this tool. It's very valuable, okay, for using Aspen for simulation, and we are going to practice it more in the next case. Okay, so let's go next. Now we are going to try the R-Gibbs model. Okay, so we're going to simulate in Aspen Plus a case study with this kind of reactor, and we are going to solve the same example of example 3, but using the R-Gibbs model instead of using the REQ model, also to discover and check the difference between them. Okay, and so this model, as we checked this thermodynamic equilibrium in Aspen Plus, and without explicitly inputting the reaction stoichiometry and calculating equilibrium constants manually, and we use an R-Gibbs reactor. Okay, so this is the main difference, and we defined the reaction in the previous model as we just saw. Okay, the R-Gibbs model calculates the final composition by minimizing the system's Gibbs free energy, and also here we have the same information that we have prepared in your last case study. Okay, and after simulating in Aspen Plus, we are going to calculate the molar fractions leaving the reactor based in the possible equations that were identified by the simulator, and also the thermal duty to keep the temperature of the reactor constant at 900 Celsius degree. Okay, so going here to Aspen, we are going to select the same compounds that we selected in example 3. Okay, so I'm not going to reproduce it again. Okay, so you know how to define the compounds. Select the Pengy-Robinson model, and also checking here for estimating the missing parameters. Okay, so going next, let's select an R-Gibbs model. Okay, we'll rename it. As our strings, they have different conditions, we will use here a mixer. Okay, for inputting the methane and the steam, and here this mixture will be fed into a reactor, and you have one output stream that could be an equilibrium of a vapor and liquid phase. Okay, so let's define first the amount of methane. Okay, and the temperature specified 400 Celsius degree, 34 bar, and let me just check here, 90 kilomole per hour. Okay, now let's define the conditions for the steam. We are going to select 280 Celsius degree, 34 bar, and an amount of 235 kilomoles per hour of steam. Okay, I think that's it. And now let's define the conditions of our reactor, calculating the phase equilibrium and chemical equilibrium. Okay, at a pressure of 34 bar, temperature of 900 Celsius degree, and also let's include our phases here as default. Okay, and we could try to identify the possible products, but in your case we're going to consider all possible products from this reaction. Okay, everything was defined. Let's click next and run our simulation. We have here results available, and we can check here in our string results first our compositions. Okay, in mole flows, for you have here produced our products. Okay, check carbon monoxide, dioxide, and hydrogen. Okay, because they were the compounds that we have selected. If you select more compounds in the properties guide that are possible products, so it will also take us into account the possibility of producing other products. Okay, because we have selected just these 3 compounds, it tried to converge as these compounds as possible products only. We have a remaining reactants without reaction. Okay, and here in vapor phase you have the amounts produced in vapor that they are equals to the total produced, indicating here that we have only vapor phase present, as our molar vapor fractions is equals to 1. Okay, And also as a block result, we need to check here as in our results the heat duty. Okay, the heat duty in kilowatts. We can check the results of amounts of energy required for keep the temperature constant. Okay, so with this simulation we solved example 4. Now in example 5 we are going to simulate a CSTR model. Okay, so let's understand our problem and let's practice it on Aspen Plus. Okay, so consider the ethyl acetate production process. Here this product for which ethanol reacts with acetic acid in liquid phase to form ethyl acetate and water via the following reaction. So this is the reaction. Here we have ethanol, here we have acetic acid, here we have ethyl acetate and water. Simulate a CSTR with a reactor temperature of 50 Celsius degree and a pressure of 101 kilopascal. Both the ethanol and acetic acid streams have a molar flow rate of 50 kmols per hour and a temperature of 20 Celsius degree and a pressure of 110 kilopascal. The reactor volume is 3 cubic meters. Calculate the composition of the product stream if the reaction rates given by, and here you have the expression, so it's a reversible reaction for which we have here a direct reaction, and the reverse reaction has a term in the driving force that's negative. Here we also have the expression for Arrhenius, for our constant of our kinetic rate. And also here we have the values for activation energy and also for the equilibrium constant for calculating the Arrhenius constant, and also here for calculating the coefficient of the reverse term for our reaction. Okay, the basis is a molar basis for the reaction, and let's consider using the non-random to liquid Hawk thermodynamic model for this system. Okay, and after finishing we will also try to implement a sensitivity analysis for changing how conversion varies with the reactor volume in this interval of half cubic meters to 6 cubic meters, considering increments of 0.5 cubic meters. Okay, so let's go to our example next. So first here we have to select our compounds, okay, and we are going to select ethanol, acetic acid, ethyl acetate, and water, okay, as selecting our compounds as we already have done in the previous examples. Okay, so we have here the structural formula, and after that let's select our metal. Okay, we are going to select the non-random to liquid for liquid phase, and for gaseous phase we are going to use the Hayden-O'Connell equation of state, okay, with Henry's law. And this is the methods that we are going to use. Let's run for estimating our properties. Okay, I think it's enough for this system. And then it will be calculating the properties for all compounds, and that also be used for equilibrium of phases calculations. Next, go to simulation, and here we are going to build this flow sheet, okay, using a mixer for mixing ethanol and acetic acid, and after we are going to use a CSTR model of a reactor for configuring our kinetic expression for our reaction. Okay, so let's build this flow sheet, and let's go next for inserting the options for the input parameters. Okay, here we have the mixer, here we have the CSTR model, and let's configure next our strings in our reactor. Okay, for ethanol, let's check here a temperature of 20 Celsius degree, and 110 kilopascal, and a molar flow rate that we can find here, considering pure ethanol in this string equals to 50 kmols per hour. For the acetic acid, let's consider here the same temperature and pressure and an equivalent molar flow rate of 50 kmols per hour, being pure acetic acid in this string. Okay, and go next. Now I think you have to configure here a reactor. Okay, for configuring the reactor, let's specify here the conditions for the reactor considering this pressure, okay, and this temperature that we have defined for the system. Also, we are going to consider only liquid phase for the reactor, and also a reactor with a volume of 3 cubic meters. Okay, so this is the unit for this amount of volume, and here we could specify different information as the residence time, for example, but we are going to specify the reactor volume, and based on the flow rate, it can be calculated, also can be calculated their residence time. So this is the volume for our reactor. Okay, let's configure the kinetics. For configuring the kinetics here in this kind of reactor, we need to import a package of reactions. So the reactions are not defined here inside the block. We define this package of reactions and we import it here. Okay, so we need to find here this folder reactions, and let's create a new pack of your reactions here, clicking in new, okay, and defining our reactions. Okay, I'm going to click here to show you how I configured this reaction, but it was a general form of a reaction, and I selected here the power law method. Power law was defined as our reaction class, okay, and we can configure here this reaction, inserting our compounds, okay, in the proper stoichiometry for the reaction. Also, we need to select here the input parameters, checking that the reaction is reversible. Okay, this reaction is active and it is reversible. We need to specify here the coefficients. Okay, 1 mole of ethanol reacting with 1 mole of acetic acid, producing here the acetate and also water. And here in the kinetic, let's configure selecting this reaction. It's the only reaction possible. We are going also to check here, reaction is reversible. And first we are going to define the direct term, and after we can specify the reversible term. Okay, so here we are going to specify the parameters for the Arrhenius law, the kinetic factor, inserting the value here for the pre-exponential term. Okay, we are going to work with the condition that temperature reference is not specified, and we are going to use this format of the equation, inserting the pre-exponential term, the energy of activation term, okay, with the information available in our case study. And we can check here the units. Okay, remember having dimensional correct units in this case. Here for the driving force term, our basis as specified in the problem is a molar basis. Okay, we are going to work with molarity here. And so our expression is a product of the kinetic factor with the driving force. So the kinetic factor is the Arrhenius law term, and the driving force is the production of concentrations in the direct reaction minus the product of concentrations for the reversible reaction. Okay, so we need to specify parameters here. First for the direct reaction, and after for the reverse reaction. Okay, so for the direct reaction, the forward reaction rate, we are going to specify the exponents of our concentration. We have here our coefficients, exponents equals to 1 for the concentrations in the direct reaction for ethanol and acetic acid, and also for our coefficient is equal to 1. So pay attention here that we are considering to calculate the constant for the direct reaction based on this expression composed by A, B, C, and T terms, and we only have the parameter for A that must be 0, because when we takes here the exponential of 0, we obtain 1 as a result for our constant 1 that's multiplying the concentrations in the forward reaction rate. So we need to specify this value here of 0 for obtaining a constant equals to 1, okay, in the direct term. But for the reversible reaction, let's pay attention that this term must be different for obtaining the coefficient of 1 divided by the equilibrium constant term. Okay, so let's change here for reverse, and for reverse we have here the exponents equals to 1 for the products, and for obtaining this value of equilibrium constant we must specify minus 4.5 as our coefficient for A. So once specified, here are conditions for this reaction. Let's the reaction is configured and it can be imported here in this guide of the CSTR model. And here we can select the reactions defined in this package R1. Okay, so this is how we configure a reaction in the CSTR model in Aspen Plus. So let's go back for our setup here. I'm just checking. We can return or we can select it again. Okay, but if you have more than one package of reactions in parallel, for example, you can select more than one package. Okay, it's possible. And going next, let me check here. I think we can play our simulation. We can run it for obtaining our results. Okay, so let's run and let's wait here for the convergence. And our convergence was obtained. Okay, as results we must check here that we have the compositions of our strings in the products. Okay, so if I click here in the product string, I can see the molar and mass fractions for all compounds in this string. Okay, and I can see here that the reaction happened and I obtained the 2-acetate and also water as products, and as the reaction is one for one, we can see that the proportion is okay. Okay, so the mass balance has also converged for this reaction. Okay, so we finished the simulation simulating this kinetics in this reactor. Here we have the results for mass fractions converting. Okay, and I think we can go now checking our sensitivity analysis. So returning here for our simulation, let's create a new case in sensitivity analysis. Okay, as we did in the previous case, this case will be named as 1. Here we are going to vary as a block variable the volume of the CSTR. Okay, so we are going to define here as a black bar because it's a variable present in the block of model CSTR. The model is the block model block CSTR, and we can, because it's a variable that normally we specify here inside the model. Okay, inside this block, it's not specified in the string. For example, that would be a string bar. Here the variable is the volume. Okay, the unit for the variable is cubic meters. The starting point is 0.5, the end point is 6 cubic meters, and the increment 0.5. Okay, next we must define the conversion as our output variable, but pay attention that the conversion is not a variable already available for selecting, so we must create this variable based on using other variables to calculate it. Okay, for example, we need to know the amount of ethanol in the input string and the amount of ethanol in the product string for calculating the conversion. So we are going to select as string variables the flow rate of ethanol in the input string, and the amount of ethanol in the product string here is named as fat and pet. Okay, and based on these values we can calculate conversion. Okay, that's a variable that I defined as local parameter, and we'll be defining it and calculating this variable using here an application of Aspen. Okay, so I selected here as a mole flow present in strings. So in the string of ethanol, I selected the compounds ethanol, the component ethanol, and here's the unity. Also, we define here the amount of ethanol in the product stream. And after defining these both variables, we must define conv. Okay, conversion is a local parameter variable. Okay, we can create it here, naming it as conv, and the type of this variable is a local parameter because it's a variable that's not automatically calculated using an output string parameter. For this, in this guide here, Fortran, we can define here considering some spaces. Okay, it's always necessary to consider the space of 9 columns. We can calculate conv using the remaining variables. Okay, we can calculate conversion being the difference between amount of ethanol entering in the reactor, represented by the fat variable, minus the amount of ethanol in the product variable, divided by the amount of ethanol in the input variable, multiplying 100 to represent it as a percentile. Okay, so here when I define conv as a local parameter, it automatically understands that this variable is defined in here in this Fortran guide. Okay, this is very valuable for creating variables that are not present in your models. Okay, in this case we are considering conversion, but we can realize that we can perform economic calculations, estimate impacts. We can insert in other equations and model here for estimating these other variables. Okay, so this is very useful for many applications. So after we defining these variables, okay, we must tabulate it. Okay, so be sure that you have defined these 3 variables here. And after that, go to tabulate and fill variables. Okay, and you can fill all variables. Normally here it fill all variables, but let's delete the other variables to not be present in our graphic. Okay, because we're going to work with the results only for this variable here, the conversion. Let's run our sensitivity analysis. And after conversion, we can plot our results, our data. I'm going to consider the volume in the x-axis, and as the response, let's select conv. And we can check here how the volume of the reactor impacts the conversion of our process. Okay, so increasing the volume, you have more conversion until some limit that will be defined here in the extremity. And finally, in example 6, we are going to simulate a kinetic reaction model considering the PFR reactor with the ArcPlug model. Okay, so let's understand our example for simulating it next. So styrene is produced by the catalytic dehydrogenation of ethylbenzene at temperature starting at 630 Celsius degree and pressure slightly above atmospheric in the presence of steam. 2 main side reactions occurs during this process: the pyrolysis of ethylbenzene into benzene and ethylene, and the alkylation of ethylbenzene producing toluene and methane. So here we have these three reactions. The first one is the main reaction producing styrene and hydrogen, and also here we have other reactions degrading the ethylbenzene in other components. Okay, ethylbenzene and water vapor enter the multitubular reactor at a molar flow ratio of 10:1. Okay, as we did in the first example, considering the ratio. Ethylbenzene, we can consider here 150 kmol per hour, and amount of steam equals to 15 kmol per hour for respecting this ratio. The reactor consists of 500 tubes, each with 4 meters long with an internal diameter of 6 centimeters. The tubes are packed with catalyst particles, and we can assume spherical particle geometry and a particle density of 2,500 kilograms per cubic meter. So this is going to impact the volume available in the reactor and in the tubs for promoting the reaction, okay, because the other part is occupied by the catalyst, and a tube void fraction of 0.45. Okay, so the remaining is considering as being occupied by particles. The initial feed temperature is 630 Celsius degree, and the initial pressure is 137.8 kilopascal. Okay, with the conditions here for the feed stream. Also, our additional information, let's use Aspen Plus for calculating the composition, temperature, and pressure profiles along the reactor. And we can see here, as it is a distributed model, and we can do that plotting some results. And the reaction rate and the kinetic parameters, they are given here. And you can see here all parameters for the kinetic rates. Here we have, for example, in the first reaction, we have here the direct term, the reverse reaction term, and here the absorption term. It's going to be, we are going to use another model specific for including this absorption term, which the Langmuir-Hushin-Watson model, okay, the L88W model. Here we have our two direct power law models for reactions 2 and 3. Here we have the Arrhenius model for reaction 1, the parameters for calculating this reverse term, the equation of Arrhenius for reaction 2, for reaction 3, the energy activations for all reactions, okay, the pre-exponential term. So we have here all information required for configuring our reaction. So we will be doing that in our example in Aspen Plus. So let's go there. So let's first define our components. So I have defined here already all components that will be used in our system, okay, styrene, ethylbenzene, hydrogen, benzene, ethylene, toluene, water, and methane, okay. As our compounds, we are going to define here as methods for properties of the compounds. Let's define here Pengue-Robinson, okay, this is the method that we'll be using in our simulation, okay. And after estimating properties, let's go to our simulation guide for defining our model for the reactor and inserting the conditions and the strings associated to that model. Okay, so pay attention if everything is selected. Okay, run for estimating properties. Okay, it's always good to remember that. And next, after conversion, let's go to the simulation guide. And here let's insert the R-plug model, R-plug reactor, okay, and present here in this palette. And let's insert two strings, an input string of mass and an output string of mass, okay, representing the feed of reactants and the output of products and reactants that didn't react. And next, let's configure our strings. First, for our feed string, let's configure here the temperature and the pressure that were given in our problem, okay, 630 Celsius degree and 137.8 kilopascal. And in our feed string, we have here an amount of ethylbenzene, okay, equals to 150 kilomole per hour and 15 kilomole per hour of water as steam that will be promoting that reaction without being part of the reaction, okay, just providing heat for the reaction. Next, let's configure a reactor and click here. Here we can specify it as a reactor with specified temperature, okay, or we can change for different operations, okay, considering a diabetic, for example. We can also select here other conditions, the constant temperature at the inlet, or we can specify another temperature for our reactor. Okay, we can change this if we want, but it depends on our process, if it's necessary or not. After here in configuration, let's select the option as multi-tube reactor with 500 tubes. The tube dimensions are 4 meters and a diameter of 0.06 meters, 6 centimeters, as we said in your system, without elevation. Okay, our reactor it is horizontal. And next, let's select here as valid phase vapor only because let's consider that there is no liquid phase in your reaction. Okay, after defining this, we need to define our reactions. Okay, as in the CSTR model, we need to define a reaction here in a folder of reactions as a package of reactions and import it here for using it in our PFR model. Okay, so let's go there to define our parameters for the 3 reactions that we will be considering. Okay, and the only difference here in this case study is that we are going to define 3 reactions instead of 1 in the same pack of reactions. Okay, so we click new for defining each one of them, and also we are going to use a different model of reaction for the first reaction, okay, as we are going to see next. Okay, let's do the configuration, okay, of our reactions. Let me find here. It is imported already, okay, but in your case, as you didn't do that yet, you must do it first, okay. We are not going to considering here pressure in the inlet of the reactor, okay, an increase of pressure. We are going to use the default conditions here in this guide, but we can configure a pressure drop, for example, and estimating it using the Ergun equation, for example. We also a possibility of considering pressure drop in reactors, okay, so this is important for this model of a reactor. We can define it here or create a correlation. And let's do the configuration next of what we need. Okay, so let me check here for the catalyst. Let's configure the presence of a catalyst in the reactor. Okay, selecting it here. Let's configure the bed voidage informant equivalent to 0.45. The particle density of 2,500 kilograms per cubic meters, because with that it can calculate the real volume available for reactants in the reactor. Okay, because with this information, the remaining of volume will be occupied by particles of catalyst. Okay, the diameter and shape factors will be kept as default. Okay, here in our configuration. And next we can go to specify our reactions. Okay, so let's run here our simulation. Let me just check if everything is okay. If our configuration is okay, we can see the results. Okay, I will give you as a challenge, okay, the configuration of the reactions. You must try to configure it in your computer considering the kinetic parameters that I pass to you in the slide. And here we have the heat duty, okay, with the amount of energy supplied for the reaction. Here in profiles of the model, we can check the variation of pressure, temperature, molar vapor fraction, and other variables. And we also can plot all these variables for checking the behavior of these variables. Let's first plot here as along the reactor length, okay, the temperature. Okay, you can check here that we don't have a variation of temperature because we selected to use the temperature constant at the inlet temperature in the model of our reactor. So the energy of the reaction is being transferred to the heat transfer system of the reactor. Next, let's plot the pressure, and we can see here that slightly is decreasing the pressure in our reactor. Okay, so this is another profile that we can see here. And also we can see, as in our profiles, we can add here a composition, for example. And when we do that, we can see selecting only our reactants, okay, and some of our products, we can define what we want to see in mass composition. Okay, I select here the 2-benzene, toluene, water, and some of them. And we can see that this reaction stops just after a few length of the reactor. So this reactor is oversized for our system. We don't need this length of reactor for
preparing this reaction. Okay, we can see that when it just entered the reaction, the reactor, the reaction happens and achieves the equilibrium and it stops. So we can see here that the most of the composition keeps constant after some time inside the reactor. Okay, but it's important that the reaction is happening. Okay, so I think you can try to configure, and if you have some question or some doubts, we can discuss later. Okay, and next, but you need to try to configure. It's not so easy, but you can to perform this connecting in your simulation. Okay.
Yes, this sounds good. Okay, thank you. So let's discuss a brief about other examples for finishing the class. Okay. So first of all, I prepared here, for example, six, for example, can you ask it about the pressure drop? Okay, and it's right. In the question, we are asking the pressure drop. So it's the difference between the initial pressure and the end pressure. Okay, so if you check here and I calculate here uh, approximately the value of the pressure in this interval and I straight in this value, we have here around this value, okay, but it depends on what point you select here. And I selected it, but this is the closest answer for measuring the pressure drop. Okay, I think it's right. Did you check it, Kenny? Yes. Okay. Thank you. So another important thing that I would like to show you is that in example 6, I left as a challenge for you configuring the kinetics. Okay, so I have already sent this file for you in our Telegrams group. Okay, and in this file here, let me just change my window just a minute here because I need to duplicate it. Okay, so in this file here, we have this general formula of kinetics for models considering Langmuir, Hushen, Wood, Hushen, Watson. That's the format of the first kinetics. Screen. It's not showing for the okay. Thank you, Mateus. I think it was appearing, but now I will change here again. Because when I change it, it stopped sharing. Okay, thank you, Mateus. Okay. Leomario said about this value was wrong in the question, but don't worry, Leomario, I will check it and I will correct it if necessary. Okay? I'm going to check this next. Um, Here, this file that I have sent to you in your Telegrams group, and here we have the general form or expression for the Langmuir-Hushen-Watson model. Okay, and also if you do not consider the absorption term is the power law expression. Okay, but in this case, this model considering this denominator term, which we call it as adsorption term because it has influence of the adsorption in the surface of the catalyst. So we are considering some effects caused by this catalyst. Okay, and in general, we have here for kinetic factor, we need to configure the Arrhenius law. Okay, the activation energy and the exponential term. For the driving force, and we have the direct and the reverse terms. Okay, if you check here, we have a direct uh, forward reaction considering 1 as the coefficient for this pressure, and for the coefficient of the reverse reaction, we have here 1 divided by the equilibrium constant. Okay, and this as we have done in example 5. Okay, so this is the coefficient for the reverse term of the driving force. And here we have this term in the denominator here, which is the adsorption term. Okay, so when you be configuring it in Aspen Plus, we must consider that this term, we must specify all coefficients that we have. If we have a pressure or a concentration of reactants or products, it's exponent, okay? And also here a general exponent for all these terms that normally we consider this as 1, okay? In our case, it is 1, okay? But we must configure it and define this value in the simulation, okay? When you select this model for reaction 1, so will be appearing these parameters for the adsorption term. And as we have done for the coefficients of the driving force, for the coefficients of each term in the adsorption term, we must specify it in the value of imperial logarithm. Okay, so we need to isolate this one using some exponential function for determining the coefficients of A, B, C, and D, but for informing both of these coefficients, which is 1 for the first term, and we don't have reactants or products multiplying it, so the exponents for all the components is 0. And for the second term, the exponent for styrene is 1, and the coefficient KST that we have the value that we must inform, we need to specify it considering here the value for the coefficient calculated by this expression. Okay, so it's necessary to estimate this coefficient using this equation, okay, for defining the coefficients in the adsorption term. Okay, so I will give you some time to try and test this configuration, and until next class, I can provide you the simulation for checking the results of this case study. Okay? Do you have other questions?
All right.
Yes? People that are online here with us, do you have questions? No? Okay. Okay, Kenny. So if you didn't finish example, say so. Don't not worry. You can try it later until next week. Okay, or answering our quiz of class 3. Here are the main references of our class today. Okay, thank you for your attention. Have a great study time and valuable learning in our course. Okay, and in next class we are going to learn and to configure some fluid phase separation equipment in Aspen Plus. Okay, so probably we'll be simulating flash drums, distillation columns, and also absorption columns, maybe an extraction if I can prepare it, and we'll be simulating this kind of equipment in the next class. Okay, so I think that's it today. Thank you again for your attention and see you soon. Bye bye.